Chemistry people, you're tuning in to section 12.3, I hope. Well, I already know who's watched the other one. Well, I don't know. Whatever. Okay, so you're following along with the notes that you got out of the packet. It's kind of a joke because some of the notes are still sitting out there in the thing, and you didn't pick up the packet. So I don't know why you're watching this if you don't have your packet, because that's what you're going to write on, and that's all you can use on the test is the notes that you take on the notes that I gave you. So I did mention before, you should stop by maybe Monday and Friday to look for work and to drop things off, please. We are educating you. And that is all. Let's continue on. We're going to be doing, let's see if I can find it. There it is. We're going to be doing chapter 12, section 3, and here's our objectives. We're going to be looking at the, ideal gas law today. Second, we're going to describe the relationship between gas behavior and chemical formulas. There's some history that you're going to read about in the book. I'm not going to spend a whole lot of time on that in this lecture. You can look it up yourself. And also Dalton's law of partial pressure, which is going to lend itself to one of the funniest things ever in chemistry, but also how you know how fast a gas is leaking. Depends on what the gas is. And then there's some stuff at the very end of the section about stoichiometry that we could have actually used the ideal gas laws, knowing a few things. We could have done some stoichiometry problems different. Not going to spend a lot of time on that either. I want to spend most of the time here on the ideal gas law. I would like you to also watch the crash course on the ideal gas law. I'll put a link in the email for that if I can remember. Something else to do. Carrying on. Let's get to the stuff, okay? I think. Here we go. There we go. Okay, ideal gas law. We had all those kind of bits and pieces of rules in the last episode. Boyle's law, giving us the relationship between pressure and volume of a sample of gas. And the rule was, well, there's going to be a summary thing here soon. That P1V1 equals P2V2. That the product of these things is a constant. We have Charles's law, which shows the ratio of these things is constant. That would be a direct variation. Gay-Lussac's law shows that pressure and temperature are directly related. And Avogadro's law is basically that the number of things in the volume is related at STP. So we've got all those that relate different things. Here's that chart here where we can see there's Boyle's law, Charles's law, Gay-Lussac's law, Avogadro's law. You need to be able to use those laws and know which one you ought to be doing. And especially what units you got to have on the temperature ones. You got to have those in kelvins, right? Okay, so that's a summary, but you can see that there's overlap here. The T1s and 2s are in the bottom. The V1s and 2s are always in the top. The P1s and 2s are always in the top. And then N, you see how it's related to volumes. It would be V over N if we were thinking before and afters. So if we smush it all together, we're going to get the ideal gas law, but there has to be a constant that's holding it all together, right? There's a constant that is the constant of proportionality between or among all of these different things that we could measure about gases. So if we think of it that way, we can change 2 or 3 settings on the dials here and predict what's going to happen to the volume or the temperature or the pressure. The only problem is this only describes, it's a very kind of pretty good summary, maybe a theory or, I mean, it's ideal gas law, right? Well, it only describes ideal gases, of which there are none, okay? So this law only describes things that approximate the real world. It's a good model, and that's about as far as it goes. So no gas perfectly obeys all 4 of these laws under all conditions. That's why STP is so important. Things are actually pretty close to ideal gas law at STP. So this is where a climate control and pressure and humidity control system in a laboratory is really, really important. So again, it's kind of like more of a curvy type of shape if we're thinking the way it works in the real world, but at some points it's really, really close. And these assumptions work well for most gases and most conditions. I'm moving my face. Here we go. It's over there now. One way to model a gas's behavior is to assume that the gas is an ideal gas, which is not true. But hey, it works. And that it's going to follow these laws. Ideal gases, unlike real gases, do not condense to a liquid at low temperatures, does not have forces of attraction or repulsion between the particles, and is composed of particles that have no volume. How do you like that? Ideal gases don't condense to liquids at low temperatures, which gases do not have forces of attraction or repulsion between the particles, which they do. That comes in handy when you're painting. And is composed of particles that have no volume, except gases do have volume. It's just, yeah. And you're like, can we just not do this section? Like, no, we actually need to talk about this. Where's the next slide I want? Yeah, I can't watch any of these, so let's keep going. In using the basic gas laws, we have to use four variables: pressure, volume, temperature, and number of moles. And then in addition to that, we will throw in a constant. Boyle's, Charles, Gay-Lussac's, and Avogadro's laws can be combined into one equation that gives the relationship between all four variables. The ideal gas law summarized as a beautiful equation: PV equals nRT. PV equals nRT. PV equals nRT. And then we have this proportionality constant. That proportionality constant, R, it depends on what the units you have for pressure. Everything else, volume, we have to use liters. Okay? Temperature, we have to use kelvins. Number of things, we have to use moles, and we'll have it in moles. But our value here for the constant, R, is either going to be 8.314 if we are doing this in kilopascals, or if the problem says they're using atmospheres, we need to use 0.0821. So you have to pay attention to what's in the problem to choose the right R value to make it all hold together. And so if you did the conversion from atmospheres to kilopascals, that would be the same proportion as going from there to there. So you have to be very careful about the number that you choose. Which one are you going to pick? All right, with that said, let's look at, oh, that's just what we just said, yeah. Units matter. Units matter. Ideal gas law describes the behavioral gases quite well at room temperature and atmospheric pressure. Again, that's pretty close to STP. Under those conditions, the volume of the particles themselves and the forces of attraction can more or less be ignored. The closer you are to STP, the closer it is that you just know that 1 mole of the substance will take up 22.41 liters of space. That's why we can kind of fudge a little bit on that when it's close. Again, because those conditions are close to STP, STP guarantees Avogadro's law that a certain amount of particles will take up a certain amount of space as a gas. 22.41 liters. Get that stuck in your head. Particles behave in ways that are similar enough to an ideal gas that you get useful results. Useful, you like that? As the volume of a real gas decreases, the particles attract one another more strongly because they're closer together, and they can be really close together, and the volume is less than the ideal gas law would predict. At extremely high pressures, the volume themselves of the particles is close to the total volume, so the actual volume will be higher than calculated. Okay, so you can see here that the curves are the way that real gases behave. The dotted line is the way that ideal gases would behave, And there's only a few places where they're close to each other. For nitrogen, you get, I don't know, it looks like it's a little bit above 200 atmospheres that you get a reading that's kind of like that, and a reading for on methane about, I don't know, 360. Now, all of them, if you drop that pressure down closer to 0 and you're using 1, the ratio PV over nRT equals 1, that's where you're going to get good readings. So, but look, the PV over nRT only varies by, 50% or whatever. Oh, I guess that's actually pretty bad. So look at the one sample problem that I really want to focus on here, and that would be, how do you go about collecting the information, then putting things in the right place? So PV equals nRT. You got to decipher this and say, where's pressure? Which thing is pressure? Tell me, which thing is pressure? Okay, 101.325 kilopascals is our pressure. Because that's true, which R do we use? Which R has units with kilopascals in it? Do you want to see them again? Which unit, which R value, that the constant of proportionality has kilopascals in it? So we're going to use 8.314 for our R value in this particular problem. PV, where's the volume? Well, it's 22.41 liters, which should tip you off to something. And then where's our temperature? But what's wrong with it? It's not in kelvins. So we have to convert 0 Celsius to kelvins, because what's going to happen if we put a 0 into an equation right now and multiply and divide? We're going to get 0, and this is going to be not helpful whatsoever. So let's gather those bits of information, right? Let's do that. Pressure 101 something kilopascals. 325, something like that. Volume 22.41 liters. Number of moles, that's what the question's looking for. We already said we're supposed to use that value for R with all its units and stuff. And then our temperature, it said 0 Celsius, but we've got to flip that over here to 273. Do we need to put the little decimal business in there? No, we're going to keep that roundy kind of like. Okay, so that's going to go right here, 273. And we want to solve for n, so these two come over here. We'll have 8.314 for R, and we'll have 273 for temperature. You know what happens when you do this problem? I mean, you don't, but maybe you should. Because 0 degrees Celsius and 101 point whatever kilopascals, it's atmospheric pressure, normal atmospheric pressure. This is like basically at STP. And at STP, if you have 22.41 liters of gas, how many moles is that? The cool thing is when the math comes out, it comes out right, and it says you should have about 1.00 moles going on there. And that's what you would expect in that particular situation. Now, the other problems that you're responsible for in your homework are going to have they're just going to have different numbers, but they go in to this equation here, and then they're going to leave one thing that's not known. You're always going to have enough information to figure out which R value to use. And then they're going to give you 3 of the other parts, and you solve for the 4th one. That's how that works. So let's just go forward a couple slides here and see how they approach that. Come on, 84. There we go. See what they did? They did what we did, except they got some weird symbols in there, and they get, yep, it ends up being 1 mole. But I could have told you that without doing the problem. Okay, so far the general behavior of gases has not been considered, and that's kind of part of the history lesson here. No calculations depended on knowing which gas was involved, but actually it does matter for a couple of things. It also it like tells us, well, their weight and density and things like that, and that's going to matter in the real world, right? Gases, one gas is denser than another. Things rise, things sink. Makes your voice high, makes your voice low, all that kind of stuff. So it is necessary sometimes to know more about a gas, like molar mass. Like, how big is it? How many of them in a certain amount of space does it matter? Yeah, like if you've got a mixture of gases in something, and then you get a hole, it's kind of important. And air is a mixture of gases, is it not? So yeah, it is going to matter some. Diffusion. Spray that bathroom spray over here, or that girl puts on some, perfume to make herself smell really strong. And then she goes walking around. People can smell it when they're close, and then eventually people can smell it when they're far away. Well, the heavier the particles, the slower they go. The slower they'll travel around through the room. The smaller the particles, the faster they'll go. Diffusion is the movement of particles from a region of high density to low density, and that's going to be faster or slower depending on how big those particles are. Gases diffuse through each other at very rapid rates. They pass by each other very quickly. But even if the air in the room is still, it would only be a matter of minutes before ammonium molecules were eventually distributed through the room. You know when somebody's been cleaning, right? And you know when somebody's been cooking bacon. All those things. So again, they go from high concentration to low concentration and eventually become mixed. But it happens at a certain rate. And yeah, so there's diffusion rates. Okay, here comes the kind of junior high humor part. You got a leak. There's that hole in your bike tire or your car tire, or I don't know, it could be anything, I guess. Gas leaks are usually bad, right? This is what you hear about gas leak. No, bad. The passage of a gas particle through a small opening is called effusion. Now, let me say that again. The passage of gas particles through a small opening is called effusion. You can call it a trump, like they do in England, or a toot, or having gas, or passing gas, or a fart. But in chemistry, we're going to call it effusion. Thomas Graham, Scottish scientist, found that at a constant temperature and pressure, again, STP, the rate of effusion of a gas is inversely proportional to the square root of the gas's molar mass. You're going to need to see a formula for that. And this law holds when one compares rates of diffusion and molecular speeds in general. Like how quickly is this leak, is all the stuff going to leak out. So on the left side of this equation here, you see we're comparing velocities of two gases, gas A and gas B. So imagine that there are hydrogen and oxygen, okay? It's just for whatever. On the left side, they got the square root of the molar masses. That's what the capital M is, of these two gases. So you look up their molar masses, and H2 would be 2.02, and O2 would be 32. And we do the math over there and take the square root. And that gives us the ratio of the velocity of one thing to the other. And again, if you know three of these things and you know the fourth, you can do the problem too. But you got to take that square root there. There's problems in the book that you'll be doing that they use effusion. Okay, so I believe the speeds and all this, came from manipulating the kinetic energy of two gases, those formulas. You can see there's 1/2 mv squared, molar mass, velocity, they're both in there. And this is similar to what we did with law of sines in math. There's a 1/2 on both sides, so we can cancel them both out. And the rest of it is just arranging ma over mb, then having the velocities together and then taking square roots. That's it, honestly. Solving the equation for the ratio of speeds gives you that formula on the previous slide. Okay? Those two formulas are related. They're related. So quick sample problem here. This is sulfur hexafluoride. If it was is it barium hexafluoride that gives you the super low voice? Maybe this is the one that gives you the super low voice. It's pretty cool. Maybe I'll link to that too in the thing. What I say? Crash course and low voice thing. You can see why a gas that's heavier, moving slower, will make your vocal cords vibrate faster, and why helium, since it's so light, make slower, I should say, for that element. And helium, which is so light, goes faster and makes your vocal cords vibrate faster, and you get a high-pitched sound. Okay, so we got oxygen molecules, and then we've got sulfur hexafluoride, and so obviously we've got to gather up some information about their molar masses. And then they give us the speed of oxygen. We're going to figure out the speed of sulfur hexafluoride. So gather our information, right? Molar mass of O2 is 32. Molar mass of SF2 is 1 sulfur, 6 fluorines, 146 grams per mole. Throw them into the equation here. One compared to the other, we've got that ratio of 32 to 146, but we got to take the square root. And so when we do the math there, we've got 480 times that ratio under the square root. That ratio comes to be about 0.47. 480 times 0.47 equals 220 meters per second. So because it's about, what is that, a fourth of the weight, oxygen compared to the hexafluoride, sulfur hexafluoride, because it's about a 1 to 8 ratio, when you take the square root of that, you get like a, oh no, it's 1 to 4. It's about a 1 to 4, and so you get about a 1/2 the velocity. To 480, half of that would be 440. It's 240. It's pretty close. It's pretty close. I would have estimated that pretty closely. Okay, lastly, it's just the history lesson here. It tells you about how they went about figuring out stuff and eventually came to what's his name's Avogadro's law. So I'm just gonna click through these slides here. If you need to pause, you can, but you should have them anyway, right? There you go. He's able to figure out what's the actual molar masses of these things. Also, when you take all the pressures of all the gases in there, you can just add them up and get the total pressure. So that's called Dalton's law of partial pressure. Each gas in there adds some of the pressure to it. We add all those pressures up together to get the total. It's explained by the kinetic molecular theory, and I'm pretty sure that that is about it. We're not going to do the gas stoichiometry, but you can check that out in your book. Okay, try to keep it short. Sorry that took so long. And yeah, so check the description for what you need to do for watching some other stuff and doing your homework. And if you have questions, you can feel free to text, call, Google Chat, or Marco Polo me. Thanks.